Hi everyone, we're Mimicker, here to introduce all kinds of knowledge, even the stuff we didn't know about. Welcome back to the Deep Dive. Today, we're not just taking a casual drive, nope. We're strapping in for a pretty thrilling, high-octane exploration into the world of Formula One race cars.
Definitely high octane.
Right. Now, when most people think F1 car, they might picture something impossibly sleek, brutally fast. Maybe even compare it to, like, the most exotic supercars out there.
That's a common comparison, yeah. You see it all the time.
But here's the core idea for our deep dive today, and it might just surprise you. F1 cars. They get mistaken for supercars, sure, but they are fundamentally something else, a completely different breed.
A whole different species, really.
Exactly. We're talking pure, unadulterated space-age technology, meticulously brought down to Earth. They're not just fast, they are, these incredible engineering marvels designed and built right at the absolute bleeding edge of what's physically, mechanically, aerodynamically possible.
That's the key, isn't it? The edge of possibility.
Totally. So our mission today is to peel back those intricate layers. The engineering brilliance, the radical design, the mind-bending physics that make these vehicles so extraordinary. We want to uncover some surprising facts, maybe even counterintuitive stuff, and really dig into the why behind their, frankly, mind-boggling performance. And also, just as important, the incredible, often unseen safety measures that protect the drivers.
Which are just as advanced as the performance bits, you know.
Absolutely. And to give you the most comprehensive, well-rounded perspective, we've pulled from a whole stack of sources. We're talking official FIA and F1 technical regulations, in-depth motorsport analyses, team blogs like Red Bull Racing's has some great insights, plus specialized engineering publications, even expert YouTube channels like Chain Bear.
Good stuff there. Really breaks down the complexity.
Yeah, so hopefully we'll get a really thorough look. Prepare for some aha moments, I think. Let's get into it.
Let's do it. And you're absolutely right. When we talk Formula One, it's not just about pushing the envelope. It's about, well, completely redefining it. The engineering philosophies, the whole mindset behind an F1 car, it's entirely distinct from even the fastest, most expensive road cars.
Also, exact.
Well, every single design choice, every component is driven by one singular goal. Extreme performance at every point on the track, every millisecond of a lap. It's not just about hitting a crazy top speed or getting a spectacular 0 to 100 time in a straight line.
Which is what most people focus on, right?
Yeah, exactly. But F1 is about optimizing for this dynamic, constantly changing environment, braking, cornering, accelerating out, managing tires, dealing with other cars. It's the whole package.
Okay, and speaking of performance, let's kick things off with what I think most people do immediately picture when they hear F1 car. That raw, explosive speed. Specifically, that incredible 0-100 kilometers per hour acceleration time.
Ah, yes, the classic benchmark.
It's widely known to be around, 2.6 seconds?
Yeah.
Which honestly sounds absolutely mind-blowing. It's often the first number people throw around to show just how ludicrously quick these machines are. But is that really the whole story? Or is it a bit misleading?
It is a mind-blowing figure, no doubt about it. And yeah, our sources like the official F1 site, motorsport.com, they consistently validate that 2.6 seconds is, an accurate and widely accepted number for 0-100 kilometers. It's seriously quick.
It really is.
However, and this is what's fascinating and maybe often misunderstood, F1 teams themselves, they actually seldom promote this specific figure as a primary performance metric in races. They certainly don't optimize their cars just for that.
Really? Why not?
Well, because while it's impressive, an F1 race isn't a drag race, right? It's not just about that initial launch. What becomes far more critical on the track are things like the car's mid-range acceleration, its high-speed pull.
Like coming out of a slower corner?
Exactly. Or accelerating down a long straight. And then there are its absolute cornering limits, how much G-force it can pull, how fast it can actually take a turn without just sliding off. And maybe most importantly for actual racing, it's braking performance. How late can you brake? How quickly can you shed speed?
Right, for overtaking and defending.
Precisely. These are the elements that dictate lap times, that enable those breathtaking overtakes, and, ultimately decide who lands on the podium. That 2.6 seconds, it's cool, but it's just one small piece of a much, much bigger puzzle.
Okay, that makes sense. It's a system, not just one number. So if these cars have, as we'll get into, well over 1,000 horsepower, why is that 0-100 kilometer time only 2.6 seconds? Shouldn't a car with that much power be even faster off the line? It feels like it should be closer to, 1 second or something crazy.
Yeah, it does seem counterintuitive, doesn't it? And that's an excellent question. It brings us right to a fundamental concept in racing, maybe the fundamental concept off the line, the traction limited start.
Tractionless. Okay.
Imagine trying to launch, say, a super powerful rocket, but you're doing it from a surface made of, like, wet ice.
Right, you just spin.
Exactly. Even with immense thrust, if you can't get grip, you just spin your wheels, literally. It's the same for an F1 car. Despite having, over 1,000 horsepower going to those rear wheels, if a driver just mashed the throttle from a standstill,
Smoke show.
big time, the rear wheels would instantly light up, spin like crazy, turning all that incredible power into, well, just smoke and noise and wasted energy. It would actually hinder acceleration, not help it. The tires simply cannot find enough grip to transfer all of that raw explosive power to the tarmac all at once from zero speed.
So it's the tires holding it back initially, not the engine.
Precisely. It's all about how much power the tires can physically transmit to the road surface at that moment. And that's why the precision needed for a perfect F1 launch is just immense. They have sophisticated electronic launch control systems, sure, but even with those aids, the driver's input is absolutely crucial.
Is that just pressing a button then?
Oh, not at all. It's about precise clutch engagement, often using paddles behind the steering wheel, and really delicate, nuanced throttle modulation. Think of it like a ballet between the electronics and the driver's feet and hands.
A very fast, very loud ballet.
Yeah, exactly. The driver isn't just flooring it, they're meticulously balancing the throttle, maybe feathering the clutch just right, constantly feeling for the absolute ragged edge of grip. They're trying to ensure every possible bit of that engine's power is translated into forward motion without breaking traction.
It's about optimizing the power delivery, not just unleashing it all at once.
Perfectly put. It's this delicate dance that turns potential energy into actual kinetic energy, actual forward movement, at the most efficient rate possible right off the line.
Okay, so the initial burst is all about managing traction. It makes perfect sense now. It's the tire's grip limit, not the engine's power limit. But then you hear about the mid-range acceleration, and that's where people use terms like the real terror, or where F1 cars really come alive. What makes that phase so astonishing? Why is that where F1 cars truly separate themselves from everything else, even the fastest hypercars?
Right. This is where the story changes dramatically. Once the F1 car overcomes that initial traction limitation, maybe gets past 100, 120 kilometers, and the speed starts to build, that's when the raw power and, crucially, the immense aerodynamic downforce really begin to work together.
Downforce. That's the magic word.
It really is. The figures here are genuinely staggering. We're talking a 0 to 200 kilometers per hour. That's about 124 miles per hour in approximately 4.8 to 5.0 seconds.
Wow. So double the speed in less than double the time from the 0-100.
Exactly. The rate of acceleration is still ferocious. And then 0 to 300 kilometers per hour, that's roughly 186 miles per hour. They can do that in around 10 seconds flat.
10 seconds to 300 kilometers per hour.
Just try to imagine the G-forces involved. The sheer relentless pushback into the seat. It's an intensity that very, very few experiences on Earth can match. It's like being constantly launched by an invisible, incredibly powerful slingshot. Even at very high speeds, the acceleration is still immense.
And that's where they leave other fast cars behind.
This is precisely where an F1 car just unequivocally leaves even the most powerful road-going supercars and hypercars utterly in the dust.
Let's use an example. You mentioned the Bugatti Chiron earlier.
Right, the Chiron. An incredible piece of engineering, no question. It weighs around 2,000 kilograms, maybe a bit more, boasts over 1,500 horsepower. A real monster. And interestingly, it can actually match or even slightly beat an F1 car from 0-100 kilometers.
Wow.
Mostly thanks to its very sophisticated all-wheel drive system and its huge road-biased tires. It can just put that massive power down incredibly effectively from a dead stop. Better initial traction, basically.
Okay, so off the line, the Chiron holds its own.
For that first couple of seconds, yes. But once you get past that initial launch phase, say beyond 100, 150 kilometers, the F1 car just vanishes.
Why the massive difference then?
Two huge factors, weight and aerodynamics. The F1 car is incredibly light, under 800 kilograms, including the driver. The Chiron is well over double that, closer to triple. That's enormous.
Less mass to accelerate.
Yeah.
Simple physics.
Simple physics, exactly. But even more important is the downforce. An F1 car's complex front and rear wings, its sculpted floor, the diffuser at the back, they're all designed to generate massive negative lift. They literally suck the car onto the tarmac.
Like an upside-down airplane wing.
Precisely. And the faster it goes, the more downforce it generates, exponentially increasing the tire's grip. This allows the car not only to accelerate harder at higher speeds, but also to corner at speeds that would send any road car, no matter how powerful, flying off the track because it simply wouldn't have the grip.
So it's not just brute power. It's intelligently applied power combined with physics-defying aero.
That's it. The aero effectively increases the car's weight pressing down on the tires, but without adding actual mass. It's genius. It lets them use the engine power far more effectively once they're moving.
Wow. Okay, so understanding this nuance, this shift from traction-limited to aero-dominated performance, it really reveals that sophisticated engineering we talked about. It's not just about a big horsepower number. It's about how that power is used across the entire speed range, in corners, under braking, the whole dynamic picture.
Absolutely.
And for anyone watching a race, knowing this helps you appreciate, maybe, why some cars are strong in slow corners versus fast ones, or why a driver might seem cautious for a lap after a pit stop.
Yeah, getting the tires working, getting the aero switched on.
Or why an overtake can happen in a high-speed section where you wouldn't expect it. It's this complete system, always working at the absolute limit, constantly pushing what's possible, that brings us perfectly from the speed to the very core, the literal backbone of these machines, the structure. And when you talk F1 structure, you have to talk about the carbon fiber monocoque. It's pretty widely known this thing costs, well, a fortune, right? Sounds like a massive investment just for the chassis.
It certainly does, and yeah, fortune is probably not an exaggeration in the context of F1 budgets. Our sources, like Red Bull Racing's own blog posts and detailed cost analyses in places like Motorsport Magazine, they consistently confirm the monocoque is indeed one of the single most expensive components on the car.
Just that one part.
Just that core tub, yeah. But it's really important to clarify the total cost of an F1 car isn't just adding up the parts list. It's vastly more complex. It includes huge amounts of dedicated R&D, computer simulations on supercomputers, wind tunnel testing, physical testing, and the incredibly specialized, often bespoke manufacturing that goes into every single tiny piece.
Right, the invisible costs.
Exactly. The intellectual property, the know-how, to give you a sense of component costs. Red Bull mentioned that a single F1 steering wheel, which is basically a tiny, powerful computer with a screen and dozens of buttons and rotaries, can cost around USD 50,000.
50 grand for a steering wheel.
Yep. And a front wing assembly, which is critical for aerodynamics and incredibly complex to manufacture, around USD 100,000. And teams might go through several of those in a season, especially if there are incidents.
Okay, the numbers are already getting crazy.
They are. So when you factor in the engine, this 1.6-liter V6 hybrid marvel, pushing over 1,000 horsepower reliably for multiple race weekends, the gearbox, suspension, everything, the total cost for one car before it even turns a wheel competitively easily rockets past USD 15 million.
$15 million for one car.
Easily. It's not just about expensive materials like carbon fiber. It's about decades of accumulated knowledge, unparalleled manufacturing precision, and just the absolute peak of engineering effort poured into every single gram, every single component.
That's an astonishing amount of money, especially when you think they might build several chassis a year and components get updated constantly. But the monocoque, it's more than just a costly structural piece, isn't it? It's literally designed as a survival cell for the driver.
Yeah.
It sounds like it pulls double-duty performance and life-saving safety.
Precisely. And this is maybe the most incredible thing about it. While it's a masterpiece of lightweight engineering, its primary design purpose, mandated by the FIA's incredibly stringent safety regulations and crash tests, is driver safety.
Safety first, even in F1.
Absolutely paramount. The monocoque weighs only about 40 kilograms, which is astonishingly light for something so strong. Think about that. 40 kilograms, maybe 90 pounds. But it's built from dozens of layers of carbon fiber weave, each layer precisely oriented to provide strength and stiffness in specific directions.
Like a high-tech composite sandwich.
Kind of, yeah. These layers are meticulously laid out, often by hand, by highly skilled technicians into a mold. Then the whole thing is cured under immense heat and pressure inside a giant industrial oven called an autoclave.
Like pressure cooking it.
In a way, yes. That process fuses the layers together, creating this unbelievably strong, rigid, and incredibly stiff structure. Its strength-to-weight ratio is phenomenal, multiple times stronger than steel, but at a tiny fraction of the weight.
But it's not just strong, it absorbs impact, too.
That's the crucial part. It's engineered not just to resist impacts like a solid block, but to absorb and dissipate massive amounts of crash energy around the driver. The carbon fiber is designed to crush and delaminate in a controlled way during a severe impact, soaking up the kinetic energy before it reaches the driver. It effectively acts like an impenetrable cocoon.
Protecting the driver inside.
Exactly, like a deformable, super strong safety cage, but made of space-age materials and designed with far greater energy absorption efficiency.
And we've seen horrifying proof that this actually works, haven't we?
We certainly have. Some truly horrific accidents have provided stark, compelling, real-life proof of the monocoque's integrity, really validating the FIA's relentless push for safety. Think back to Romain Grosjean's unbelievable crash in Bahrain in 2020.
I remember that vividly. The fire.
Horrifying.
Yeah.
His car hit the barrier at immense speed. It literally split in half. The fuel cell ruptured. Massive fireball. Yet the monocoque, that survival cell, remained fundamentally intact. It protected him from the initial impact forces, pierced the barrier, and allowed him to miraculously extract himself from that inferno with relatively minor burns considering.
It was unbelievable he walked away.
It truly was. And then there was Zhu Guanyu's terrifying crash at the British Grand Prix in 2022. His car flipped upside down after contact, skidded at terrifying speed across the track and gravel, dug in, and then vaulted over the tire barrier, ending up wedged against the catch fencing.
Just terrifying to watch.
Again, the monocoque, including the halo head protection device which is integrated into it, held absolutely firm. It protected him from the massive G-forces of the impacts, the abrasion from sliding upside down. And again, incredibly, he walked away effectively unharmed.
These aren't just theoretical tests, they're real-world proof.
Absolutely direct testament to the incredible strength and design philosophy of the modern F1 monocoque. Without this level of protection, the outcomes in those crashes, and many others, would have been utterly catastrophic. It's truly a life-saving device that allows drivers to race at the limits they do.
It's incredible to think something so light can be so protective. It really reframes what safe means at 300+ km/h. Now, connecting the costs we talked about and the fact that even these incredible structures can be damaged, there are pretty significant strategic implications for the teams, right?
Yeah.
Especially now with the sports cost cap. It's not just a physical hit, it's a financial hit.
Indeed. This brings in a whole other layer of complexity, the economic reality of modern Formula One. Since 2021, and refined since, F1 operates under a strict cost cap. For 2024, it's around, USD 135 million per team.
Which sounds like a lot, but covers almost everything.
It covers most operational expenses. Car development, manufacturing, logistics, most personnel salaries. It's a tight budget for teams operating at this level. So what this means is, a crash doesn't just break expensive parts and rack up an immediate repair bill.
It hits the budget cap directly.
Directly and deeply. If a monocoque is damaged beyond repair, which can happen in severe impacts or even other major expensive components like the floor, gearbox, or wings, that money has to be spent on replacements. And crucially, that's money pulled directly from the same limited pot that was allocated for research, for designing and building upgrades, for improving the car's performance later in the season.
So crash today steals performance from tomorrow.
That's a perfect way to put it. It creates significant long-term consequences for a team's performance trajectory and their entire development plan. Imagine a team has a major aero upgrade package scheduled for 3 races down the line, something they've invested heavily in. A big shunt early in the season may be damaging a chassis or requiring multiple new front wings. It can completely derail that plan. Those funds are now diverted from future performance gains to immediate repairs just to get the car back on track.
Ouch. That could cost them points, positions, maybe even championship contention later on.
Absolutely. It can potentially hamstring their competitiveness for the rest of the year, forcing really painful choices about where to allocate remaining resources. It puts immense pressure on drivers to bring the car home clean, and it forces teams into this constant balancing act, balancing aggression and risk-taking on track with the very real, potentially crippling financial consequences of an accident.
It adds a whole new dimension to the strategic chess game of F1. It's not just about track position, it's about budget position too.
Definitely. Every decision has ripple effects.
So the carbon fiber monocoque, it's this fascinating dual-role component. It's the pinnacle of lightweight performance engineering, enabling the speed and agility, and it's this critical life-saving cocoon for the driver. And on top of all that, its cost and vulnerability under the budget cap rules deeply impact team strategy and season planning. What a complex, high-stakes piece of kit. Okay, from the car's core structure, let's shift focus now to what really gives it its punch, the engine, or more accurately, the power unit these days. One of the things people always talk about with F1 engines is the incredibly high rev limits. Just how high are we talking, and why is spinning it so fast absolutely crucial for getting F1 level performance?
You're right, the revs are central to the whole F1 power unit philosophy. Our sources, like the official FIA technical regulations and detailed tech docs from teams like Mercedes, AMG, Petronas, confirm that under the current rules, the hybrid V6 turbo era that started back in 2014, the maximum engine speed is strictly limited to 15,000 revolutions per minute.
15,000. 50,000. Just say that again. That sounds insane compared to a road car.
It is pretty wild. Most road cars, even sporty ones, might redline somewhere between, 6,000, maybe 8,000 RPM if you're lucky. An F1 engine spins at nearly twice that speed. That's incredibly fast for an internal combustion engine, especially one that has to be reliable enough to last for multiple race weekends under extreme punishment.
So why? Why spin it so incredibly fast? What's the benefit?
Well, the why boils down to a fundamental physics equation for power. Power equals torque multiplied by RPM.
Okay, power equals torque x speed.
Exactly. Think of torque as the twisting force the engine produces, like how hard you can turn a wrench. RPM is how fast the engine can apply that twisting force, how many times per minute it completes a cycle. Now, F1 engines, by regulation, have a relatively small displacement, only 1.6 liters.
That's tiny, like a small family car engine.
It is tiny in capacity. So to extract the immense power they need, we're talking over 800 horsepower just from the combustion engine part, they have to spin it incredibly fast. High RPM is how they compensate for the small displacement to achieve that monumental power output.
So they make up for lack of size with sheer speed.
Precisely. Every single component inside that engine, the pistons, the connecting rods, the crankshaft, the valve train, they're all made from exotic, incredibly lightweight but strong materials. They have to withstand enormous forces and stresses generated by operating at such extreme rotational speeds, lap after lap, race after race. It's a real testament to cutting-edge materials science and precision engineering, pushing the absolute limits of what a combustion engine can physically endure.
Wow. Now, something a lot of longtime F1 fans talk about, sometimes complain about, is how today's F1 engine sound is so different from past eras. It's a really common observation. Can you explain that sound evolution? What technically changed to make them sound, well, less screamy?
The sound debate. Yes, it's a really interesting point and definitely one that sparks a lot of passion among fans who remember the older engines. The sound signature of an F1 car has definitely evolved significantly over the years.
How would you describe the difference?
Well, today's hybrid V6 turbo engines with that 15,000 RPM limit, they produce a sound that's often described as maybe higher pitched, more complex, sometimes a bit whiny or buzzy due to the turbocharger and the hybrid elements. It's still incredibly loud trackside, don't get me wrong, but it's a different character of sound. Compared to the truly iconic vicious shriek or banshee wail of the older, naturally aspirated V10 engines from the early 2000s. Those things revved up to an astonishing 19,000 RPM.
19,000?
Yeah. Or even the V8s that followed them, which peaked around 18,000 RPM. Those engines produced this incredibly high-frequency, piercing scream that many people just associate intrinsically with the raw power and drama of F1.
So what caused the change? Just the lower RPM limit?
That's a big part of it, yes. Fewer firing pulses per second naturally lowers the fundamental frequency. But it's also directly tied to the regulatory changes in engine configurations. Moving from V10s to V8s and then crucially to the current 1.6-liter V6 turbo hybrid format in 2014 fundamentally altered the acoustics.
How does the turbo and hybrid part change the sound so much?
The turbocharger itself plays a huge role. It sits in the exhaust stream and uses the hot exhaust gases to spin a turbine, which in turn spins a compressor to force more air into the engine. That turbine spinning at incredibly high speeds in the exhaust bath acts like a very effective muffler. It absorbs a lot of the raw acoustic energy, the sharp pressure pulses that used to escape directly out of the exhaust pipes in the naturally aspirated V8 and V10 eras.
So the turbo muffles the scream.
It dampens it considerably, yes. Plus, the complexity of the energy recovery systems, the hybrid bits, also influences the exhaust flow and sound. It's a direct consequence of the sport's necessary shift toward greater thermal efficiency, fuel economy, and relevance to road car technology, even if it meant sacrificing some of that iconic, raw sound that many fans loved.
A trade-off for efficiency and progress, essentially.
You could say that. Balancing raw power and spectacle with efficiency and technological advancement.
And speaking of that hybrid integration, it's not just the 1.6-liter combustion engine doing all the work anymore, is it? There's a pretty significant electrical boost contributing to that total 1,000-plus horsepower figure we mentioned. How does that electric power get generated and deployed.
Absolutely. The hybrid system is fundamental to modern F1. It's not just bolted on, it's deeply integrated. The key component here is the MGUK, that stands for Motor Generator Unit Kinetic.
MGUK.
Okay. This is essentially a powerful electric motor generator connected directly to the engine's crankshaft. Under braking, instead of all that kinetic energy being wasted as heat in the brakes, the MGUK acts as a generator. It harvests that energy, converts it into electricity.
Like regenerative braking in an electric car.
Exactly the same principle, just far more powerful and efficient. This recovered electrical energy is stored in a sophisticated, relatively small, high-voltage battery. Then, when the driver wants a boost for accelerating out of a corner, defending, or attacking, they can deploy that stored energy. The MGUK instantly switches functions, becomes an electric motor, and delivers a powerful burst of extra power directly back to the crankshaft.
How much extra power are we talking?
The MGUK alone contributes approximately 160 horsepower or 120 kilowatts. It's a significant chunk of power delivered instantly. So you combine that with the 800 plus horsepower from the combustion engine.
And there's your 1,000 horsepower total.
Pretty much, yeah, well over 1,000 horsepower for the whole power unit system working together. Now, there's also another part, the MGUH motor generator unit heat. This one is connected to the turbocharger. It recovers heat energy, waste energy from the exhaust gases spinning the turbo.
So capturing energy from heat too?
Clever? Very clever, but also incredibly complex and expensive. It helps keep the turbo spinning, reducing lag, and can also generate more electricity for the battery. Though it's worth noting, the MGUH is actually set to be removed in the next generation of F1 engine regulations starting in 2026, mainly to simplify things and reduce costs.
Interesting. So it's a constantly evolving system.
Always. This integration of hybrid tech isn't just about adding horsepower, it's about incredibly sophisticated energy management. Drivers and teams have to strategically decide when and how to harvest energy and when and how to deploy it for maximum performance throughout a lap and throughout the entire race. It makes F1 a crucial testbed for advanced hybrid technologies that eventually trickle down to road cars.
So what we're really seeing with the power unit is this fascinating balancing act. Extracting huge power from a tiny engine via extreme RPMs, integrating complex hybrid systems for boost and efficiency, which in turn changes the very sound of the sport. It's this constant push and pull between raw performance, fuel efficiency, reliability, and even the whole sensory experience for the fans. An incredibly complex symphony of mechanics and electronics.
That sums it up perfectly. A technological marvel, really.
Okay, that power has to get to the ground somehow. Which brings us to maybe the most critical interface between that complex car and the actual track, the tires. And it's clearly not just about having four round black things sticking the car to the road, is it? There seems to be an incredibly precise operational requirement, especially around temperature. Keeping them in the perfect zone sounds like a constant battle.
You've absolutely hit on one of the most critical and often, I think, underestimated aspects of F1 performance. It's genuinely an art as much as it is a science. Our sources, especially Pirelli Motorsport, they're the sole tire supplier, so they know their stuff. They confirm that the recommended operating window for the dry weather tires is incredibly narrow, typically somewhere between 90 and 110 degrees Celsius.
90 to 110 C, that's pretty hot, and only a 20-degree window.
Exactly. It's not just a guideline. It's the absolute sweet spot. That's the temperature range where the specific rubber compound they've designed is intended to offer its maximum grip, its peak performance. Go outside that window, either too cold or too hot, and the tire's ability to generate friction, to physically hold that incredibly fast car to the road, it just drastically diminishes.
So it's not just about pressure, it's all about hitting that temperature target.
Precisely. Understanding how to generate that temperature, how to maintain it, and how to manage the tires within that narrow window throughout a race stint. That truly is an art. It goes way beyond just inflating them correctly. It's this dynamic, constant challenge involving the driver's feeling and inputs, the car's setup, and the strategists on the pit wall interpreting streams of data. Honestly, it's often the difference between winning and losing.
Okay, so if that 9110 is the ideal window, what happens if the tires get too cold? How do drivers even fight against that during a race, say after a pit stop or during a long safety car period?
Yeah, cold tires are a major hazard for drivers. This happens most obviously right after a pit stop when fresh, cooler tires are bolted on, or during those extended periods driving slowly behind a safety car. The tires literally cool down, the rubber compound stiffens up considerably.
And they become
Drivers often describe them vividly as feeling like plastic or like driving on ice.
Okay.
They offer very, very little grip. This makes the car incredibly difficult to handle, especially at the limit. Braking distances increase massively, cornering speeds drop right off, and the driver just has no confidence in the car. It feels unpredictable.
So how do they warm them back up quickly? We see them weaving side to side.
Exactly. That weaving looks dramatic, but it's absolutely purposeful. When drivers weave aggressively like that, especially on the outlap from the pits or just before a race restart after a safety car, they're not just trying to warm the tires with ambient air or speed. They are actively generating friction, intense friction, by scrubbing the tire surface laterally against the tarmac. This friction forces mechanical work, mechanical heat, directly into the rubber compound, trying to bring them back up into the optimal 90-110-degree window as rapidly as possible.
It's a very deliberate physical process then.
Oh, absolutely. It requires immense skill and sensitivity because pushing too hard on cold tires can lead to a spin or a lockup, but not pushing hard enough means you lose crucial time and track position. Every fraction of a second lost while the tires are coming up to temperature can make the difference between gaining a place or losing one, or worse.
Right, so that's too cold. What about the other end of the scale? What happens when the tires overheat? And what causes that?
The perils of overheating are just as detrimental to performance, sometimes even more so because the damage can be longer lasting within a stint. Tires can overheat for several reasons. One common one is following another car too closely for too long.
How does that overheat them?
When you're tucked right up behind another car, you lose clean airflow over your own car's wings and bodywork. This reduces your aerodynamic downforce, meaning the car relies more on mechanical grip, and it tends to slide around more on the tire surface. Less downforce also means less cooling airflow reaching the tires themselves. Also, just driving in the turbulent, hot air coming off the car in front heats them up.
Okay, so falling closely is bad for tire temps. What else?
Excessive sliding through corners, maybe the driver's pushing too hard or the car balance isn't quite right, generates a lot of surface friction and heat. Locking up the brakes heavily also puts immense localized heat into the tire surface. When a tire gets too hot, beyond that ideal window, its complex rubber compound can start to break down physically.
Break down how?
It typically manifests in two main ways, which you can sometimes even see on TV coverage: blistering and graining.
Blistering, graining.
Blistering is when the heat deep inside the tire core causes gases or parts of the rubber compound itself to form bubbles that push outwards towards the surface. You end up with these small, often hard blisters on the tread, which effectively lift sections of the rubber off the road, severely reducing the tire's contact patch with the track.
So less rubber actually touching the road, less grip.
Exactly. Graining is slightly different. It happens more when the surface overheats due to sliding. Chunks or strips of rubber start peeling off the tire surface because of the combination of heat and shear forces. This torn rubber then often readheres to the surface in clumps, almost like eraser shavings sticking together.
Also sounds bad for grip.
Very bad. Both blistering and graining lead to a significant, often sudden, loss of grip. The car becomes unpredictable, braking efficiency plummets, cornering ability suffers, and lap times just fall off a cliff. And the real problem is, once a tire starts to seriously overheat and either blister or grain, it's incredibly difficult for the driver to recover its performance within that stint without significantly backing off the pace and managing it very carefully, which of course no F1 driver wants to do.
So managing this temperature window is absolutely crucial for strategy.
It brings us right to the strategic core of almost every single F1 race outcome. Teams have to constantly predict tire degradation rates based on the track, the conditions, the car setup, and the driver's style. They monitor tire temperatures and wear in real time using sensors and telemetry data. All this information feeds into deciding the perfect pit stop timing.
When to come in, what tires to put on.
Exactly. Deciding when to pit, which tire compound to switch. The softer compounds are faster but wear out quicker and are more sensitive to heat. The harder compounds last longer but offer less peak grip, and then advising the driver on how aggressively they can push on those new tires. These are absolutely fundamental strategic calls.
Decisions made in seconds based on tons of data.
Made in fractions of a second, often, based on a torrent of live data and complex prediction models run by the engineers on the pit wall. And these decisions, getting the tire strategy right or wrong, frequently determine the final race result. It really proves that F1 races aren't just won by the fastest car or the bravest driver, but often by the team and driver who can best understand and manipulate their rubber throughout the race distance.
So what look like just simple tires are actually incredibly complex dynamic components They demand constant, precise management, deep strategic foresight from the teams, and this incredibly delicate touch and feedback loop from the driver. It really is an intricate art and, yeah, often the key decider between winning and losing. It highlights just how much calculation and precision goes into every single lap, every decision, even down to the micro level of keeping those tires happy in their little 20-degree window.
Couldn't have said it better myself. It's absolutely central.
We've covered the structure, the powerhouse engine, the critical tires. Now let's talk about the driver's direct connection to all of that, because it's clearly not just about pressing buttons and turning a wheel like in a video game. And here's a fact that I think genuinely surprises a lot of people when they first hear it. Formula One cars, despite all their incredible power, speed, and mind-bending technology, they lack traditional power steering. I mean, my everyday road car has power steering. Why on earth don't these multi-million-dollar machines?
That is a truly fascinating detail, isn't it? And one that really highlights the unique nature of F1. Our sources, like those great technical breakdowns from Chain Bear on YouTube or articles in specialist mags like Race Car Engineering, they absolutely confirm this. F1 cars do not have a typical power-assisted steering system, hydraulic or electric, like you find in virtually every single road car built today.
So nothing helping the driver turn the wheel.
Essentially, no. The system in an F1 car is pure mechanical linkage from the steering wheel to the front wheels. Now, that doesn't mean it's crude or basic. It's incredibly highly optimized, engineered with ultra-precise gearing, low-friction components, everything designed for maximum efficiency and feel. But that fundamental power assistance, that feeling of effortless turning you get even parking a normal car, it's completely absent in an F1 car.
Why? What's the reason? It seems deliberately making the driver's job physically harder.
It does seem counterintuitive at first glance, but there's one paramount, absolutely non-negotiable reason for sticking with a pure mechanical system in F1: raw road feel, unfiltered feedback.
Feedback, okay. Tell me more.
Drivers rely completely on the unfiltered, direct sensory information coming back through the steering wheel from the front tires. This feedback tells them exactly what the tires are doing, how much grip they have, and crucially, when they are approaching the absolute limit of adhesion. Every tiny vibration, every subtle shift in the car's balance as it loads up in a corner, every nuance of the tire's traction. It all communicates vital information directly to the driver's hands.
It's like their primary sense for what the car is doing underneath them.
Exactly. It is their primary feedback loop for controlling the car at the limit. Power assistance, whether hydraulic or electric by its very nature, would filter out or dampen some of that incredibly subtle but absolutely vital sensory input. It would make the steering feel lighter, yes, but also number, duller, less communicative.
And at 300 kilometers, numb is the last thing you want.
Precisely. For an F1 driver operating on the absolute knife edge, trying to differentiate between maximum available grip and being just a hair's breadth away from a massive, potentially catastrophic slide, any filtering of that crucial feedback, any delay or obscuring of that conversation between the tires and their hands would be, frankly, a lethal trade-off. They need to feel exactly what those front tires are doing second by second, millisecond by millisecond. They need to know precisely when the tire's on the verge of breaking away, how much more steering input they can apply.
So it's about maintaining that direct, unvarnished connection between the human and the machine's limits.
Absolutely essential for the precision and control required to drive these cars at 10/10.
Okay, feedback is king. Are there other reasons too? Practical ones?
Yes. Beyond that critical feedback aspect, there are also the ever-present practical considerations in F1: weight and reliability.
The usual suspects.
The usual suspects, exactly. A hydraulic power steering system with its pump, fluid reservoir, lines, and actuator, or even a modern electric power steering motor and control unit. It would add unnecessary kilograms to the car. And in F1, where engineers fight tooth and nail to shave off every single gram,
Every gram counts.
every gram absolutely counts towards performance. Adding several kilos for steering assistance is just seen as unacceptable weight penalty. Furthermore, any additional complex system, hydraulic or electrical, introduces more potential failure points.
Something else to go wrong.
Exactly. In F1's intense, high-stakes, millisecond world, where races are won and lost by the tiniest margins, and every single component is pushed to its absolute breaking point, any additional system that could fail is viewed as an unacceptable risk. Simplicity, where it directly contributes to performance, like feedback and reliability, is almost always preferred, even if it means a significantly more demanding physical task for the driver.
That makes a lot of sense. Prioritizing feel, minimizing weight, maximizing reliability. But how on earth do the drivers manage the sheer physical effort? especially in those tight, low-speed corners where there isn't much aerodynamic help. I just imagine it must be incredibly brutal on their upper bodies.
It is precisely as brutal as you imagine. And this really underscores the extreme physical conditioning required to be an F1 driver. They are phenomenal athletes. There's a really stark difference in the steering effort required at different speeds, which is another one of those fascinating F1 paradoxes.
How so?
At slow speeds, think in navigating the incredibly tight hairpin turn at Monaco or wrestling the car through a slow chicane. The steering is incredibly heavy. Drivers have to apply sheer, raw, muscular strength to turn the wheel. These are the moments where you can often see on the onboard cameras the veins popping in their necks, their forearms straining. It's a testament to the immense physical effort involved.
Why is it so heavy at low speed?
Because there's very little aerodynamic downforce pushing the car into the track at those speeds, so the driver is manually having to overcome the immense mechanical grip generated by those incredibly wide, sticky tires just through brute force. It requires significant strength just to muscle the car around the corner.
Okay, so low speed equals brute force. What about high speed?
Now, paradoxically, at high speeds through fast, sweeping corners like Eau Rouge at Spa or the Maggots-Beckett's complex at Silverstone, the situation changes dramatically. It becomes less about brute strength and much more about incredibly fine control and sensitivity.
How does that work?
This is where the car's massive aerodynamic downforce really comes into its own. As the car builds speed, the wings and floor generate hundreds, even thousands of kilograms of negative lift, literally squashing the tires harder and harder onto the road surface. This dramatically increases the available grip.
Right, we talked about that. But how does it affect steering effort?
Well, this huge vertical load on the tires actually, counterintuitively, lightens the steering effort required for a given steering angle, despite the enormous lateral G-forces the driver is experiencing. The tires are so loaded up, so keyed into the track surface, that the steering becomes incredibly responsive, almost fingertip light in relative terms.
Lighter at high speed. That seems backwards.
It does, doesn't it? But it allows for those incredibly precise, ultra-fine inputs from the driver. A tiny flick of the wrist, a minute adjustment on the steering wheel, can translate into a significant, precise change in the car's direction at 300 kilometers. So it's this amazing contrast. At low speeds, it's all about wrestling the car with strength and endurance, while at high speeds, it becomes this incredibly delicate dance of micro-adjustments and surgical precision, feeling the absolute limit through your fingertips.
Which means F1 drivers need this unique combination of raw power and incredible fine motor control.
Exactly. World-class strength, stamina, endurance, and the fine motor dexterity and sensory feedback processing of, say, a neurosurgeon, all while dealing with massive G-forces and making split-second decisions.
Wow. So this lack of power steering really deepens our understanding of the whole human-machine interface in F1. The driver's direct, physical, unfiltered connection to the car, their reliance on that raw sensory feedback. It's prioritized above almost everything else, even driver comfort or reduced effort. It just hammers home the extreme physical and mental demands placed on these drivers. They're not just controlling the car, they are an integral physical component of its operation, constantly interpreting and reacting to every tiny vibration, every subtle shift. It really makes you appreciate the sheer athleticism involved behind the wheel even more.
It truly does. They are elite athletes in every sense of the word, operating perhaps the most sensitive and demanding machines on the planet. #tag concluding thoughts.
So wrapping this all up, what does it all mean? We've really taken quite a deep dive today, haven't we, into what makes these Formula One cars not just fast, but truly fundamentally a different breed of machine.
Yeah.
So far removed from anything else on four wheels you're likely to encounter.
Absolutely. I think what we've explored today really hammers home that initial idea. F1 cars are the absolute epitome of space-age technology brought down to Earth. They are not just faster supercars, they're bespoke, purpose-built racing instruments where every single component, every single design choice is ruthlessly optimized in this relentless, almost obsessive pursuit of marginal gains right at the very edge of what physics allows.
Yeah, relentless feels like the right word.
It is. We've seen the real nuance in their acceleration, how it's less about that initial headline number and far more about that sustained, brutal, mid-range acceleration enabled by lightweight and incredible downforce, leaving even the mightiest hypercars far behind once rolling. We've delved into the incredible, carbon fiber monocoque, this revolutionary structure that's both a cornerstone of lightweight performance and an absolutely essential, life-saving survival cell for the driver, and how its immense cost and vulnerability now have profound budget implications under the cost cap, directly shaping team strategy.
Got it.
We've unpacked the heart of the beast, those high-revving, incredibly power-dense hybrid power units, marvels of engineering extracting over 1,000 horsepower from just 1.6 liters, combining combustion and sophisticated electric energy recovery, and how their very sound has evolved alongside the technology.
Yep, the sound debate.
We've explored the intricate, almost black art of tire management. We're operating within that tiny 20 degrees Celsius temperature window, understanding degradation, and making those split-second strategic pit stop calls so often decide the final race outcomes.
The tires, so crucial.
And finally, understanding that direct, unfiltered, physically demanding connection between the driver and the machine, made possible by the surprising absence of power steering, really underscores the extraordinary physical skill, sensitivity, and mental processing power required from these elite athletes.
It all paints a picture of incredible complexity and synergy.
It truly does. It's this constant innovation, this relentless pursuit of tiny marginal gains, and this incredible synergy, this fusion of cutting-edge engineering, fundamental physics, strategic thinking, and supreme human skill, all required just to make these machines perform consistently at the absolute limit, lap after lap. It's what makes Formula One such a unique spectacle. The car is just as much a hero, a product of genius, as the driver piloting it.
So, thinking ahead then, here's a thought for you, our listeners, to ponder, building on everything we've discussed. Given this relentless, almost fanatical pursuit of speed, safety, and now efficiency in Formula One, how might the next generation of these space-age vehicles continue to push those boundaries? What breakthroughs are still out there? And perhaps more intriguing for everyday life, what future everyday technologies might emerge from this crucible of extreme performance, just as things like carbon fiber traction control and hybrid tech have done in the past?
That's a great question. F1 is often a glimpse into the future of automotive tech.
It really is. So the next time you watch an F1 race, or maybe just see highlights or read an article about these incredible machines, we really hope you'll look for some of these details we've talked about today, the way they accelerate out of corners, the driver's inputs, the tire strategies playing out. Hopefully, it enhances your appreciation for the sheer genius, complexity, and drama behind every single lap.
Hopefully so. There's so much going on beneath the surface.
Thanks for tuning into this episode. If you enjoyed our content, don't forget to like, subscribe, and turn on the notification bell.